Welcome to Mastering Solutions. They give us this figure here, which of course is a single slit diffraction grading pattern. And they tell us in the question that we're dealing with a single slit. We're told that lambda, let's go ahead and write it down, is 500 nanometers, 500 times 10 to the negative 9. And the screen is 1 meter behind the slit. So L in this case is 1 meter. We're asked what is the width of the slit, and we have to put it in millimeters. So the equation that we can use for this is y is equal to p times lambda L over a. Now remember, with single slits, p is referring to the distance from the central max out to a minima. So the first order minima and the second order minima. It's not to the bright spot. So for this one, you can use p of 1, and we'll use the distance from here to here. So the central max out to the first order minima is half of a centimeter. So this is 1 centimeter, so half. So p for the question will be 1, and y, which is that distance we just talked about, is half of a centimeter. So 10 to the negative 2 meters. Now in the equation A, that is what the width of the central slit is. So that's what we're trying to solve for. So let's rearrange this equation for that. So we'll multiply both sides of the equation by A, and we'll divide both sides of the equation by y. So that gives us, if we come over here, A is equal to P lambda L over y. And now we have everything, so all we have to do is plug and chug. So A is equal to P, which we said is 1. Lambda is 500 times 10 to the negative 9. And L, we said, is 1 meter. So really just 500 times 10 to the negative 9 meters over, we said, half of a centimeter. So 0.5 times 10 to the negative 2 meters. And so we have 500 times 10 to the negative 9 over half of a centimeter, and that gives us 1, 2, 3, so 0.1 millimeters, or 10 to the negative 3. And so that is our answer here for the slit spacing on the single slit question, 0.1 millimeters.